AC or DC? Edison or Westinghouse? A look at the real battle of technology behind the movie The Current War and how that fight affects our current war over fossil fuel. Up next on Science Goes to the Movies. Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Lisa Beth Kovitz. Today we're looking at the current war, and we've got the electric company in the house. Damian Sciano is Director of Distributed Resource Integration at Con Edison, where he oversees the company's evolving plans to integrate renewable energy into the traditional electric distribution business. Welcome to the show.
Thank you, Lisa Beth. I'm really charged up to be here and talk about this very exciting topic. As you know, not only was the big revolution between Edison and Tesla, but nowadays electricity is just as important. We're trying to make it greener, more reliable for our customers. So it's a very exciting business to be in now, and it's a very exciting business to talk about its origins.
The war in the current war is the battle of Thomas Alva Edison's DC current versus George Westinghouse and Nikola Tesla's AC current. So let's start with the basics. What's the difference between AC and DC current?
Sure. Let me start with direct current because I think it's a little bit easier to explain. Basically, when you turn on the light switch and you're getting DC current, you go from, say, 0 volts to 100 volts, and you get a steady 100 volts of DC. And the current, maybe 1 amp, you get a steady 1 amp of current. And, quite frankly, I think a better name might have almost been, steady current, because that's what it is. It's just a direct line. Alternating current, as the name implies, alternates between positive and negative values. So when you turn on the switch, you're starting out at 0 volts. You're going up to, say, 140 volts in the example I gave in a comparable example to direct current, down to negative 140 volts, back up to 140, et cetera, and so on, 60 times a second to produce the same amount of electricity as that direct current does.
Why is that better?
It's actually easier to generate AC electricity than it is to generate DC electricity, as counterintuitive as that is.
So let's talk about how electricity is made, because electricity is not pulled down from the heavens with a key and a kite string. It's manufactured with magnets based on the interaction of coiled copper wires spinning inside an electromagnetic shaft. So how different is that process from, say, shuffling across a shag carpet in fuzzy slippers?
Great question. Basically, there's no magnet involved when you're shuffling across the shaggy carpet. What you're doing is you're simply producing a charge on yourself, which is called static electricity. And then as we all know, when you find a sibling to go shock, you touch them and you discharge that charge that you built up. But there's no magnet involved in that, like there would be with current, what's called current electricity and the generation of power.
So this magnet spins around the copper coil. Mm-hmm. How is that producing AC current, or is that producing DC current, or is it just producing current?
Right. When the magnet spins inside the copper conductor, it's producing alternating current, and that was really one of the greatest innovations, in my opinion, of our modern society. There's 4 kinds of forces. There's gravity. There's weak and strong nuclear forces, and then there's electromagnetic phenomena. And as the name implies, there's this interplay between magnets and electricity that Michael Faraday kind of discovered in the 1800s and really kind of exploited by realizing that as long as you spin that magnet inside of a conductor, you're going to get electricity. Pretty much any way that you can spin that magnet is going to produce the AC power for you. So you could get a hamster spinning around and a squirrel, running around in his little cage, or more practically, and certainly at the beginning of the whole electrical revolution, maybe you'd have a hydro dam spinning basically a pinwheel that's attached to a magnet. Very quickly, it became easier to burn a fossil fuel and make steam that would turn that spin wheel. And because hydro resources don't exist everywhere, that was much, much easier, and that's certainly what we've seen proliferate. Nuclear power can also be used to make that steam. And even some of the newer and more exciting renewables like wind power are used, and they essentially do the same thing. They spin this magnet.
Do they spin the magnet, or do they create the steam that spins the magnet?
Right. Well, the wind turbine itself spins the magnet. So in that case, simply the wind blowing across the blades that are designed and tilted and adjusted just to optimize that wind speed, get the turbine to spin, and that turbine essentially spins a magnet.
And what about DC current? How do you make DC current?
Right. DC current is actually a lot harder to make. And the irony even of the movie is that the DC power that Edison made came from AC. He was spinning a magnet, and then he was doing what's called inverting the AC, and he was kind of creating this funky looking wave that had the effect of being DC. Back in Edison's time, I think the only way you could really make pure DC power is to, build a battery and take advantage of the potential difference between two chemicals, and that would kind of force an electron through the conductor, and that's how you'd get your DC electricity. But as soon as that potential dissipates, that's the end of your DC power, and it's very costly and expensive and difficult to do that on a large scale.
And it doesn't travel. We learned from the movie that DC doesn't travel very
Right,
far.
and then you've made all that effort to generate the DC power, and then you can't transmit it very far at all. That's correct. So for all those reasons, even to get DC power back then, you had to make AC power. What's kind of cool today is, the solar photovoltaics in particular actually do produce DC power. And then ironically, we have to have an inverter to invert it back and put it onto the AC system. So, it's a very interesting twist, and certainly an interesting time to, be around and see where the next level of things goes. And then that power is much more applicable, that DC power is much more applicable for use with computers and things like that. Things that didn't exist 120, 130 years ago when they were making some of this.
Fascinating. Mm-hmm. That's fascinating. Nikola Tesla has become something of a folk hero in pop culture, in part because the photographs of him are so very cool. But we don't spend much time talking about what he actually did. In the current war, we see that he improved the motor that made AC current safer and Westinghouse profitable, and I think it's got something brilliant to do with magnets. So Damian, talk to me about polyphase induction motors.
I would be happy to. That's a very good question. I think Tesla's innovation was twofold. Probably the most innovative thing he realized was that a motor was just a generator in reverse. So whereas you're spinning a magnet in a generator to make electricity, you can take that electricity and spin a magnet in a motor, and then attach that magnet to whatever you're trying to spin, a pinwheel or et cetera, and so on. And while that might sound obvious today, it was anything but obvious, and it was an extremely elegant solution. It meant a lot more components, a lot less components to the motor, so it was much cheaper to manufacture. It performed much better, and it had much less maintenance because, again, it had less pieces. So that was the first part of the innovation. The second part was realizing that if you use three phases, which is what you mean by polyphase, in this case the poly is three, you could set the alternating current on three different wires, so they'd be different phases, but they would react in the same way, and you kind of build this beautiful equilateral triangle around a magnet, and now you can cut down the amount of inductors you need in half. You can improve the performance of the motor pretty dramatically, and you can get much more power out of it. So, first part of the innovation, realizing the motor was just a generator in reverse. And then the second part was really optimizing it with this three-phase power to give it even lower cost and better performance.
Yeah, we talk a lot about the elegance of science.
Yes.
and the beauty
Yes.
of the genius, and it's so like art, it's just delightful.
That three-phase power in particular is really like art, I must say. It's absolute balance and performance.
So why does AC current hum? And why is it in America it's B flat and in Europe it's in G?
That's a really fascinating question. It's funny, right? Because if you did listen to the plug to your light, you wouldn't actually hear it hum. But you're absolutely correct that when you go to a substation, you can hear the equipment humming, and it's because that alternating power is creating a vibration in the machinery, and that vibration is the same as if you plucked a guitar string, say. So in the U.S., when you effectively pluck that guitar string, you're doing it at 60 hertz. Now, I couldn't carry a tune if it had a handle, so I had to look this up for you. But I am told that the 60 hertz system in the U.S. produces that, you said B flat, right? And the European system, they run at a 50 hertz, so they choose to make their sine wave change plus and minus 50 times in a second, and that has the tone of a G, from what I understand.
The movie implies that Edison didn't like AC current because he didn't think of it first, but also that AC was stronger and therefore more deadly. In actuality, is AC more deadly than DC?
I mean, both of the technologies are deadly. And it was a funny part in the movie when the assistant kind of admitted that to those investors. You know, he had enough integrity that he didn't want to leave them with the idea that DC couldn't kill people. What Edison kind of exploited was that transferability of AC power, that you can transform it and get from a low voltage to a high voltage and a high voltage to a low voltage very easily, so that he was kind of making a high voltage to make it easier to electrocute the horse and ultimately human beings. But the wrong set of DC current through your body is going to kill you just as easily as the wrong set of alternating current. So it was a little bit of a smoke and mirrors argument.
Well,
yeah.
He has that reputation.
Yes.
He does. Thomas Alva Edison invented the light bulb, except that he didn't. No one person did. Humphrey Davy invented electric light without the bulb in 1802, but the exposed carbon-based filament burned too quickly and, interestingly, too brightly for practical use. In 1840, Warren de la Rue put a platinum filament in a vacuum tube, creating an efficient but much too expensive design. In 1850, Joseph Wilson Swan was the first to put the light into the bulb, and in 1874, Henry Woodward and Matthew Evans filed for the first patent for an electric lamp made of glass cylinders filled with nitrogen and carbon rods. In 1878, Woodward and Evans sold that patent to Thomas Alva Edison, who continually improved on it until sometime in 1879, when Edison and his team lighted upon carbonized bamboo. The filament extended the life of a light bulb over 1,200 hours, or about 50 days, and so, passing through the hands of many scientists, the light bulb was born. So how much time do you think had to pass between the invention of the electric light and the beginning of the change a light bulb joke?
Well, I am sure it was actually very little time, and if you tell me that it took 50 days for that first light bulb to burn out, I suspect it was 50 days. In fact, I even wonder if there was a little period of time where the candle makers were picking on the light bulb changes.
You think they began the change a light bulb joke?
That's right. That's exactly right. I'm sure it started with how long does it take to change out a candle or light it.
Well, one of the reasons those change a light bulb jokes are so universal is because electricity is everywhere. Light bulbs are everywhere. Do you think at a certain point we just take electricity for granted because it's become so universal?
Yes, yeah, I do think so. I think people are starting to think about it almost the same way they think of oxygen and water. It's something that's vital to the quality of their life. And, certainly when we have these big storms and things like that, we see just how much hardship it creates to go even a couple of days without electricity. So that's why Con Edison, our focus is always on making the system as reliable as possible. We're constantly trying to use new technologies, better analytics, greener power to kind of achieve that. But yes, it's even increasingly, as important as it is to our customers today, it's even increasingly more important as each day moves on and technology keeps driving us to more and more electronic devices and things like that.
And what's happening with the light bulb? Because, someone from Con Edison came knocking on my door trying to give me free light bulbs, it was just extraordinary.
Yes.
What's happening with light bulbs that we need to change them all?
Sure, that's part of the initiative Con Edison and other in the industry are taking to kind of make the system more efficient. Because if you can use the electricity more efficiently, you don't have to generate as much. It makes for a cleaner society. So the light bulbs in particular, the LED lights, are dramatically less power than the incandescent bulbs, and even a good deal less than the compact fluorescents that some of you might be familiar with. That was kind of the transition of the two.
So ugly.
Yes, they are. Yes. And not always the best lighting quality, but they were kind of probably primed the pump for better efficiency. And now the LED lights are really, I think the consumers love them. They make, like I said, they use the electricity so much more efficient. so we don't have to generate as much power. And quite frankly, the cleanest electron you use is the one you don't have to use. So energy efficiency is always a lead for us in terms of a more sustainable future.
Is that a joke engineers tell each
It is
other?
a joke. I'm sad to tell you that I've heard that many times. In fact, there's an entire book written that's called First Fuel. And it's actually, I think the point it makes is that the first fuel should be not using fuel and just being more efficient.
Oh, interesting,
Yeah.
interesting. Thomas Edison brought electric light to New York City in 1882, and the backbone of Manhattan's electric grid was so firmly formed around Edison's DC current that it took until November of 2007 to convert the last DC system in New York City to AC. That's 125 years. How massive are these systems?
That sure is, yeah. I mean, if you think how pervasive it is, it's going from a generating plant, it's going under the streets, it's going under every street, and it's going into every building. So it's very hard to undo something like that. I got to admit, I checked the facts, I checked you on your facts, and I was surprised it took us till 2007. I thought we did it a little bit sooner than that. But the reality is, as I mentioned, those wires and equipment stay in the ground for decades and decades. They work reliably. And in a lot of cases, the customers were very satisfied with the product they had, and they didn't want to spend time, money, or effort changing it out. So it took a long time to convert them all over to AC once it was there.
And you can plug the same fridge into DC as you can into AC.
No, you really can't. But what you can do is you can take the AC and you can start replacing it in the streets and then putting what's called a rectifier into the building, and then the customer still gets DC. But because of all of the innovation we talked about with Tesla's motor, you couldn't use the AC. You couldn't run a DC motor on AC electricity without some kind of rectifier in between.
That's fascinating. In the movie, The Current War, Edison and Westinghouse are fighting over the type of current the United States should have, but the real-life ramifications of that war are much deeper than the movie states because they were also fighting about who was going to build the country's electric grid. Does that exact 1890s electric grid that we see being built in the movies, is that what we have now?
A large portion of it is what we have today, yeah. I mean, some of the beauty of the electrical system is that you put it in there, you bury it in the streets, you hide it behind the walls, and you can count on it to work for decades and decades and decades. It's actually very reliable. It has a very long life. Like I mentioned before, we still want to bring any kind of new technology to bear, so certainly we change out the equipment with better equipment. We're constantly driving improvements in asset management, and monitoring is something that's changed dramatically since Edison's times. I mean, they kind of put it in and let it run like that. We're looking at those, the loading on the circuits very closely, the loading on the transformers. But yeah, some of the basic components are still pretty much what was put in the ground today.
So, our electric grid is made up of the generating plant, the transmission lines, the substation, the distribution lines, and the transformers. No, not these transformers. These transformers. Did I miss anything?
Well, of course you did, Lisa Beth. The customers, which are our most important part of the grid, and in fact the whole reason we exist, right? And they're kind of directing to us the power that they need to live their everyday lives. So we've seen that kind of move from wanting just reliable and affordable power to wanting reliable, affordable, and green, sustainable power. So Con Edison is doing our best to be a leader in that. We've actually got a business development subsidiary that our clean energy businesses actually are the second largest solar producer in the country. And we're constantly looking for ways to innovate in our traditional business also with energy efficiency, integrating solar and wind and batteries into our grid, and ultimately giving the customer what they want. And that's going to, in the future, that's actually going to mean charging electric vehicles, probably for everybody at some point, and maybe moving their boilers over to electric heat pumps and kind of actually electrifying their lives even more than it is, believe it or not.
What fuel turns the magnet that generates the electricity that we have now, and what can we, and by we I mean you, what are we doing to change over that magnet, change over that turn to more sustainable fuel sources?
Yeah, great question. Again, historically, kind of some of the first and easiest things to turn that magnet was hydropower, so like the Hoover Dam. Huge project for the U.S. in terms of construction, but also in terms of getting the energy. Some of the hydro dams over on the West Coast drove the steel manufacture and the airplane making of World War II. But obviously that couldn't scale and move very easily, whereas coal and oil and natural gas could. So pretty quickly, those became the dominant fuels that were used to be lit up and and ultimately heat water to make steam, and steam to turn the turbine. So that drove a lot of growth and economy, but it obviously had a negative impact on the environment because of the release of the CO2 and the other pollutants with that. So what you see today is a desire to kind of move to cleaner ways of spinning that. So wind is kind of easy to see, right? You can see how wind would spin a magnet the same way that some of this other stuff would. So wind is one of the newer and more effective ways. Offshore wind is particularly exciting, even for New York City, where space is at a premium if we can do this in the ocean and then bring it onto the land. And then even the first solar generators were actually reflectors. I'm sure probably everybody's seen that picture. They were reflectors that reflected the sun's light and heated up a salt kind of fluid to spin a turbine.
So basic.
It's so basic. It's so basic. And then the innovation came with photovoltaics, and where now it's kind of just taking the sunlight and just passively producing direct current electricity. And as I mentioned, the irony is we got to now convert that DC to AC to make it go through the rest of the grid. But those two technologies in particular are very exciting about kind of leading the green power revolution. And then one of the pieces you also are going to need with that is you're going to need more energy storage, because obviously the sun doesn't shine all the time and the wind doesn't blow all the time. So kind of got those pieces going.
But as long as we can spin the magnets.
Yes. Or in the case of photovoltaics, move an electron through a conductor.
Or move an electron
like a
through
direct
a conductor. We can still use the same grid that we saw beginning to be built in the current war.
Yeah, I'm obviously biased working for a transmission and distribution company, but that does seem to be the way that it's playing out. There was initially a question of whether you could go completely wireless by putting, solar panels on your house and a battery in your garage. Could you completely cut from the grid? It doesn't look like that's the best way to do it for most people, especially in an urban setting. Where you're in an apartment building, you may not have a lot of rooftop space. So while I think that distributed energy resources like that's kind of the buzzword for it, are still going to be an important part of the equation, it looks like large-scale renewables like that offshore wind that I mentioned are really going to drive the energy revolution of the future. And those are not only going to go through the same transmission and distribution system, but we're likely going to actually have to enhance our existing transmission and distribution system to deliver it.
Really?
Yes, especially, again, think of the New York City. I tend to be a little New York City centric, but you're probably not going to have wind turbines on even some of our amazing skyscrapers. So you're going to be taking the power from further upstate New York than we currently produce it today. So now you've got to transmit more power through that corridor.
Right. Same
Same thing with offshore wind. They're talking about putting those offshore wind turbines about 21 miles south of us. So that means you're going to need 21 miles of wire to bring it into our substation. We're going to have to expand our substations because they're certainly not ready to take that. And then we'll probably even have to reinforce our system to take all that additional power.
Because distance matters with electricity.
Yeah, distance definitely matters. Yeah, and that was really the benefit of the AC power, is that you could raise up that voltage so high and kind of deliver it a long distance and then step it down. But I will say the innovations now with it's called HVDC, high voltage DC systems, where they can now get the same effect and raise the voltage on a DC system and run it through a simple concentric conductor.
Really?
Oftentimes under waterways like the Hudson River. We've got some of these in the Long Island Sound, believe it or not. This kind of HVDC power will actually help drive those distances too. So even DC is starting to become part of the transmission solution.
Circles within circles within circles.
Yes. There's a lot of, you keep coming back to some of the same points and questions and issues here.
Yeah.
Yeah.
Okay, I have a silly question. That is totally silly. I was watching a horror movie, and it occurred to me that the horror movie trope of the electricity going spooky when something spooky comes on. What actually makes the lights flicker and the electricity go spooky. What's happened?
Right.
Let me put it this way. What happens when a ghost gets into your electricity?
Well, thankfully that doesn't happen a lot, but usually it's a function of the voltage dropping for one reason or another. So oftentimes, it's actually not very often.
When a ghost gets
Yeah,
into your
yeah.
electricity, he messes with your voltage?
Yeah, there's some, the balance of the system is out of balance. So there's either not enough generation on the system to meet the load at the time, so the 60 hertz will actually slow down a little bit, and that would create some flicker. The other thing that could happen is there's some resources on the system that are causing the voltage to be a little bit low and depressed, and that's where you'd see the lights kind of dim a little bit. So you wouldn't typically see that in an extremely urban place like New York City, because we've got so many lines, we've got so much redundancy.
So
but
few ghosts.
So few ghosts, right, exactly. Exactly, but if you were on an island somewhere
Right.
where there's just
Right.
not a lot of transmission lines feeding in,
Right.
there's probably only a handful of generators as opposed to dozens and hundreds and thousands like we have in New York State and New York City. That's where you'd more frequently see that kind of ghost effect and lights kind of flickering and going down.
So on the creative side of somebody looking for an idea, it's really not so off the wall that if I know we're talking supernatural and silly, but if that silly supernatural haunting came in, he would suck the electricity out of your thing.
Yes.
Go screenwriters.
Right, exactly.
Damian, thank you so much. We are out of time.
Oh, okay.
Thank you for spending time
Yes,
with
it's
us.
been a pleasure. Thank you so much, Lisa Beth. Appreciate that.